Imagine you're an Iranian military planner in early 2026. Your forces rely on distance as a natural barrier. Proxy militias, drone swarms, ballistic missiles launched from hundreds of kilometers away. Suddenly, videos appear online. Massive C-17 Globemaster IIIs touching down in the Gulf, ramps dropping, and AH-64 Apache attack helicopters rolling off, rotors folded, ready to be spun up in hours. Why does this shift the equations so dramatically? Because physics imposes a brutal constraint on rapid force projection. You can't teleport heavy combat platforms. You have to fight gravity, air resistance, and structural limits just to move them. For decades, getting attack helicopters like the Apache into a theater quickly enough to matter has been one of military logistics' hardest engineering problems. In the escalating 2026 Middle East conflict, following U.S. and Israeli strikes on Iranian targets beginning late February, the battlefield has become a drone and missile saturation game. Iran and its proxies launch waves of low-cost Shahed 136 kamikaze drones, forcing defenders to burn through expensive interceptors or risk infrastructure hits. The economic driver is clear. Each Patriot missile costs millions, while a Shahed runs tens of thousands. Defenders need a cheaper, more flexible counter. Enter the AH-64 Apache. Unlike fixed-wing jets that need long runways and burn fuel circling, the Apache is a hovering gun platform. It loiters at low altitude, uses electro-optical targeting to identify small, slow drones, and engages with a 30mm M230 chain gun, or APKWS rockets. Recent footage from UAE and Israeli Apaches shows them downing Shaheds mid-flight, precise, low-cost intercepts that preserve high-end SAMs for ballistic threats. But getting Apaches there fast is the bottleneck. Ground shipping takes weeks across hostile seas. Sea transport risks mines or strikes. Airlift is the only option for speed. That's where the C-17 becomes the hero. Visual, side-by-side comparison. C-17 cargo bay dimensions versus AH-64 with rotors folded. Animated loading sequence. The Apache weighs about 10 metric tons fully loaded, with a folded width of roughly 5 meters and length around 18 meters. The C-17's cargo bay is 26.8 meters long, 5.5 meters wide, 3.8 to 4.1 meters high, designed precisely for outsized loads like this. But here's the physics wall. Lift must equal weight plus drag during takeoff and cruise. The C-17 uses 4 F-117 PW 100 turbofans, each producing 40,000 lbf thrust. Total thrust-to-weight ratio hovers around 0.34 when fully loaded, modest for transport. To lift 77 plus tons, max payload 500 kg. It relies on high-lift devices, leading-edge slats, trailing-edge flaps, and externally blown flaps where engine exhaust blasts over the flaps to increase dynamic pressure and delay stall. Visual, CFD animation of airflow over C-17 flaps during takeoff, color-coded pressure contours showing boundary layer energization. Why blown flaps? Boundary layer separation kills lift at high angles of attack. By directing high-velocity exhaust over the flaps, you re-energize the boundary layer, allowing steeper climb angles and shorter takeoff rolls, critical for operating into austere fields near conflict zones. Without this, you'd need runways 50% longer, limiting basing options. Yet the constraint bites hard. Each C-17 can carry only 2 AH-64s, sometimes 3 in extremis with careful loading, rotors removed or folded, tails detached in some configurations. To deploy a meaningful squadron, say 12 to 16 Apaches, you need multiple sorties. Fuel burn skyrockets. The C-17 guzzles for 5 tons per hour at cruise. A trans-Pacific or transatlantic leg with aerial refueling pushes efficiency limits. Visual, exploded 3D view of C-17 cargo bay with tie-down points, Apache secured, time-lapse of real unloading footage if available, or animation. Boeing solved the outsized cargo problem with a clever compromise, a high-wing design for propeller/rotor clearance, though jet-powered. rear ramp with kneeled landing gear for easy roll-on/roll-off, and computerized load planning software that optimizes center of gravity in real time. The Apache itself aids the process. Folding rotors reduce frontal area by over 60%, tail folds sideways. Ground crews use hydraulic mules and specially designed fixtures to secure it against 3G maneuvers. Once on the ground, reassembly takes hours, not days, thanks to quick-release pins and modular avionics. This system isn't magic. It's applied first-principles thinking: minimize frontal area to cut parasitic drag, maximize structural efficiency to handle point loads, and use directed thrust to cheat the lift equation during takeoff. Nothing's free. The C-17's versatility costs dearly. Unit flyaway price around $220 to $250 million each, far more than older C-130s. Fuel efficiency lags behind dedicated strategic lifters like the C-5M. Payload range trade-off means more refuelings for ultra-long hauls. For the Apache, air-to-air drone engagements expose it to MANPADS or small arms fire at low altitude. The 30mm gun is devastating against drones but limited to 1-200 rounds. Reloads require forward basing. Maintenance is brutal in desert heat. Turbine blades face sand ingestion, composites degrade under UV, hydraulics leak under thermal cycling. Visual, graph, cost per drone kill. Patriot missile $4M versus 30mm rounds, $100, $200 per burst, versus Apache sortie cost, $20, $30K/hour including fuel/maintenance. The math favors the helicopter for low-end threats, but only if you can sustain the logistics chain. In 2026, this C-17 to Apache pipeline is viable and battle-proven. Deployments to the Gulf demonstrate rapid reinforcement can shift deterrence. But it's not cheap. Each Apache runs $35, $40 million, plus sustainment costs in a hot war zone. For the US and allies, it's sustainable. For smaller forces, it's a stretch. Ultimately, this is human ingenuity pushing against physics' hard limits. Gravity doesn't negotiate. Drag is merciless, and entropy ensures every system wears down. Yet by understanding those limits, then engineering clever workarounds, we turn impossible distances into hours. In a region where seconds decide survival, that's not just logistics. It's strategy written in thrust, lift, and compromise. Thanks for watching. If you enjoyed this breakdown, hit like,